Okay, so this video is not about buffers for your car, but maybe buffers for biology. So as you can see in your blood, there is a very tight range of pH, and you have about 3 buffers, different types of buffers in your blood, because if your pH of your blood goes too high or too low, you won't make it, and that goes for most living things. So what is a buffer? A buffer is something that resists pH. So it's made up of a weak acid and its base, or a weak base and its conjugate acid. And so we'll look at how that works. So here's some just simple examples. So vinegar is a weak acid, ammonia is a weak base. And so sodium ethanoate, the H plus comes off and gets replaced with an Na. And this one here, a H plus joins to, a Cl joins to the ammonia ion. So this is the salt here of the weak base, the conjugate acid of the weak base, and this is the salt here of the weak acid, or the conjugate base of the weak acid. So this is how the system works. So here, this one here is, we're giving an example of an acid buffer. So what happens when you add acid? This will completely dissociate and you'll have H pluses come off. And because it's a strong acid, it will not have any tendency to interact and go back. And so the excess acid here will join up to this salt here. And because of that, that will now join this system here, but most of it stays in this way. So the pH does change slightly, but most of it is absorbed by the salt and turns into the weak base. And as we mentioned in the previous video, weak bases are actually very good at holding, weak acids are very good at holding onto H pluses, and weak bases are very good at holding onto OH minuses. So the excess H plus, you could consider with Le Chatelier's principle, increases this side, therefore it pushes the equilibrium to the left and increases this amount, and so the system stays relatively stable. The same thing happens with when you add base. So this is a strong base, so this will come off. This will then get absorbed by this here, and so that will potentially lower the pH, but equilibrium will establish, and this will lower and get pushed to the right, thereby producing more H pluses to compensate for the H pluses that have disappeared because the OHs have taken them away. So the equilibrium is pushed to the right due to the loss of H plus, and so the pH remains the same to some degree. Okay, so it's not exactly the same, but it certainly resists it and keeps it fairly stable within a range to a point. Okay, so you need to be able to explain that. So I've written these sentences here because students have trouble working out what's going on. So hopefully that slide is helpful. What you also need to remember too is you need to have enough of the weak acid and enough of the salt. This is because if you didn't add the salt and all you had was the weak acid here, as soon as you add too much OH minuses here, it'll take out all of the this here and lower it. You'll soon run out of this, and so if you don't have enough of the acid, you won't be able to maintain the pH you want. In a similar sense, if you don't have enough of the salt, and then when you add H pluses here, the H pluses will soon not have enough salt to react with to turn into this here. So the various concentrations of the salt that you add and the acid that you add are important. You need lots of acid so that you can maintain the pH by creating more H pluses. You need lots of salt, and so that it has the ability to remove a lot of the H pluses. Now, explaining buffers in the base as bases is exactly the same. You have a weak base with its plus the salt of the weak base. So we've got ammonia and we've got ammonium chloride. It could be anything like ammonium nitrate. Choose something that's not reactive, the anion side of it. So I've just tried to do it a different way, this time with diagrams, just to emphasize what's going on. So because it's a weak base or weak acid or whatever, most of it's here. And so what happens when you add the acid is this will neutralize and get rid of the OH and move the reaction to the right-hand side. and so the NH3 will react with the water and replace the OH to keep the constant. And in the reverse, because you can see it's a weak base, or weak acid if it was a weak acid, there's hardly any of this. So there's not much of this if you add OH minus to get absorbed and turned back to NH3. So that's why we add this salt. So there's a reservoir here, a store of it. And so when you add OH minus, there's plenty of it to react with how much, well, to that limit anyway, of OH minus. And so that will push it to the left-hand side, therefore removing the OH minus. So hopefully that will get rid of, help you understand it a little better as well. The syllabus specifically says that there are no buffer calculations required, but however, these are really good for your SEs. So there's very many interesting and simple ways to do experiments. So if you are doing, thinking of something to do for a science experiment, it's very interesting to change factors or add factors and see what the effect is. So you might need buffer capacity for that. So it's just as a very simple equation. So it's the amount of acid or base that changes the pH by 1 is the definition of a buffer capacity. So you could see the effect of something on the buffer capacity. There's just a simple example down here. So you don't have to get it to change by 1. You just measure any change and convert it to a per 1 by dividing it by the pH. And if you want to know what the pH of a solution will be when you add various different amounts of acid or base, just go to the Henderson-Hasselbalch equation. Just Google that. Okay, so this extra is definitely not one of the extra ones that they slip into the exam, but it is an extra for making some very easy and interesting science experiments.